Okay, first, what in the hell's an evolute? Well, an evolute is the locus of centers of curvature of a curve. Now, right here, we're looking at a circle. There we go. And the evolute of the circle is that point at the center of the circle called the center. A circle has a single radius. Oh, what's happened to my pointer? Oh, I don't know. Maybe I'll use the other one. So a circle has a single radius and a single center, and is constant curvature. We need to remember that the radius is always perpendicular to the curve at the point where it intersects. And it's also tangent to the evolute. In this case, it's tangent to the center, and in fact intersects it as well. So what if the curve's not a circle? Well, here's an ellipse. And you can watch the perpendiculars to the curve repeat all the way around. Let's go on to the next slide, and this tells you where to find this thing on the web. Okay, so the I've stopped the animation here, and we can look at it. You can see that there are there are four heavy blue lines around here and a whole bunch of perpendiculars to the curve. The heavy blue lines are the evolute of the ellipse. Now I'm going to be talking a lot about conic sections today, and I'm going to talk mostly about circles, ellipses, parabolas, and hyperbolas. If you're an ATM, you think mostly in terms of spheres, ellipsoids, paraboloids, and hyperboloids. They're more or less interchangeable for this tester. Okay, what about a parabola? Well, there's one. The point P on the parabola has as its center of curvature the point C on the red curve. The red curve is the evolute of the parabola. This side of the evolute is the locus of centers of curvature of this side of the curve. Parabola, you will remember, is the only curve that all by itself reflects light, parallel light, that's light that comes from stars and stuff, to a focus. And so a lot of telescope makers have figured their mirrors to paraboloidal figure, which is presumably the gold standard, but it has a few drawbacks, and we'll get into those. All right, now, the evolute is discernible from either side of a curve. The curve here it's a surface, and this side represents the concave side. So the glass for this would be on this side of the curve. This one represents a convex curve, so the glass over here is on this side of the curve. I'd like to call to your attention the fact that the evolutes are identical. Same surface, same evolute. The circle in the middle is the best circular fit to the parabola at its apex. Okay, so whether we draw these lines from the right or the left doesn't much matter. We can get an evolute either way. Okay, now here's a bit of a video, and I'm not sure how I start this. What do I do? Click. It's a standard video. Yeah, there you go. This is an attempt to explain what an evolute is. I have a red curve here, which is a parabola drawn by Derived for Windows, a mathematical program that I use. I have here a line of little brads driven into the wood here, And they are driven along the line of the evolute of this parabola. Okay, I also have a pair of strings, one attached to this nail here, and one attached to the farthest nail here. If I take this string and stretch it to the apex of the parabola here, its end will trace a circle naturally. You know, a circle has a single radius and a single center. That's the center. This circle has in common with the parabola that it is the radius of curvature of the parabola right at this point. Now, if I take the other string, that's this one, and make sure it's nicely wrapped around this line of nails, and I stretch it out to the parabola here, it will get the other one out of the way.
I wanted to get Tom Cruise to do this, but
if I unwind it from its evolute, the end of the string where my thumb is traces the parabola, like that. Now, a couple things we should notice here. One is that the string is always perpendicular to the curve that it traces out. That's point one. Point two, it is always tangent to this evolute. Another thing we should notice is that the difference between the parabola and the circle is this much, whereas the difference between the radii of curvature of the this part of the parabola, which is part of the circle, and this part is in actual fact about this much from here down to here. This gives us an amplification factor. So the two curves differ by this much, but the radii differ by this much. And that amplification factor permits us to get a better measurement because it's stretched out more. Okay.
Okay. How do we go further on this? All right, well, let's go back one. No, let's go back. Okay, so these are the points to remember. The evolutes derive from the curve. If we've got the evolute, we can reproduce the curve. It doesn't matter which side of the curve the glass is on. And the evolute magnifies the variations in the curve. Let's talk about conic sections. Here's a 60-degree cone, and it's cut into 5 parts. Some of you have seen this in ATM1, not as brightly colored, but it's there.
There's a model of it up in the pink clubhouse.
Okay, cool. So here we have a circle, which is the green portion. Here, tiddlywink shaped, an ellipse. Here, bright red on my screen, but not so on here, is an hyperbola, and then a parabola, and here's an hyperbola. The hyperbola and the parabola are open curves, as we know. You don't have to cut off half of the whole curve to get reflections from it. And the hyperbola is the only curve that would have a second part if we had another cone stood point down on this one with the axes coincident. The circle and the ellipse are closed curves. All right, now let's look at what the evolute of a conic might look like. Come on, all right. We've got, every conic has a property called its eccentricity, okay? A circle has an eccentricity of 0. An ellipse is between 0 and 1. A parabola has an eccentricity of 1. And the hyperbola has an eccentricity of more than 1. And this expression right here describes all 4 curves in terms of the eccentricity and the center radius. And the evolute is expressed like this, except we can't do that for a parabola because its eccentricity is 1. Now the diagram's a little busy, but it's color-coded. The circle circle's red and its center is red, although you may have a little trouble seeing that. The ellipse is blue, and it has an eccentricity bigger than 0 and less than 1. And its evolute is blue as well, a little curve here. The parabola is green, and it has its evolute here. And the hyperbola is cyan, and its evolute is here. Now, we can also get expressions for the evolute of a Schmidt corrector or a Schmidt-Cass. And yeah, these eccentricities bear a relationship to what angle you cut the cone at, but I'm not going to talk about that because I can't remember it, and it's not really relevant here. Okay, I have a computer program that does all of this, so I don't need to worry about it, and you don't either if you want to do it. Okay. Anybody got any questions? Okay. All right. So let's go on to the next one here, and let's talk about the speed of optics. We have on top an f4 lens. We have on the bottom an f1.5 lens. And I've been asked why a fast optic creates a hotter spot than a slow one. And I had to think about it a while. It's not that a point source is going to cause burning, make smoke come out of the paper, that kind of thing. It's because we don't have a point source. If we're focusing the sun on a piece of paper, this lens is going to make a bigger circle of the sun than this one. And therefore, it's going to be hotter. Okay, fast and slow, what we have is a focal length and a diameter, both lenses. The focal length divided by the diameter is called the F ratio, and a low F ratio, small F ratio, is a fast lens because it puts more light on a piece of film, and therefore you have to open the shutter shorter. Sorry if I'm preaching to the choir here. Okay, now we're at the cusp of the thing here. How do we get an optically perfect surface? We don't. Perfection is a province of religion, not optics. And if you don't believe me, just listen to the ATM cuss when he gets a scratch on his mirror, or when the mirror slides off the lap and breaks on the concrete floor. Okay, here we have some tolerances. How did they do that? Let's see, okay. Here we have some tolerances, and some of them are pretty bad. Plowed field, 5 wavelengths out or worse. We can't use that for anything but demonstration of what's a bad figure. So you could maybe get a headlight out of something that's 2 wavelengths. Now, the tolerances in wavelengths are here. The same measures in nanometers are here, and millionths of an inch are over here. Okay, so we can get okay for an amateur telescope at an 1/8 wavelength, or 70 nanometers, or 2.76 millionths of an inch. If we want to go professional, commercial, we want to do a little better, that's a 20th wavelength. And if we really are hankering for something very, very good, a 100th wavelength is something we might shoot for. We're not going to get a 100th wavelength out of an f1.5. We can do, perhaps, with the Evolute tester, a 20th wave. So let's talk about methods of testing. Here's our old friend, Jean-Bernard Léon Foucault, the inventor of the Foucault pendulum and the knife edge test. And here's his test. And I presume that some of you at least have crouched by the edge of a table and stared past a razor blade at indistinct shadows. Foucault's test gives us probably a 1,500 times magnification of the variations in the mirror. And we need that because the variations are so small you can't measure them with a screw or anything comparable. Foucault's test can only be used on concave mirrors, those that focus incoming light. And for a convex mirror, it's worthless without a great deal of ancillary equipment, flats and Hindle spheres and that kind of stuff, which I got to admit I've never used. Well, here's the next guy we talk about here is Vasco Ronchi, who invented the Ronchi test, and some Ronchi-grams over here. And using either of these tests, we can get to about an 1/8 wavelength. And presumably, we might be able to do a little better if we've got a good micrometer or digital readout or something, but not a whole lot. So if we want to do any better than that, let's look at the Evolute test. It shows a much finer measurement precision. Amplification is nearer to 5,000 for slow mirrors. Mirrors at f1.5 can be measured to about a 28 nanometer or 20th wavelength. And the convexity or concavity of the surface doesn't matter, since the Evolute is, as we saw before, the same for a concave or a convex surface. I've got coffee problems. Oh, good. No. Maybe I should. Well, I'll see if I can cough it out and get rid of it. All right, with an Evolute tester, the telescope maker doesn't have to stare past a razor blade at indistinct shadows, because the laser, when you cast it on the mirror, is reflected back, and we can work the slope of the laser so as to get the exact, oh, thank you, the exact perpendicularity we need. Okay. Also, the tester that I've built does it under computer control with an Arduino card. Okay, so let's see, where do I go? Okay. Using an Evolute tester, we could make all three surfaces of a Schmidt cast. The spheres might be pretty easy. Oh, hey boy, I'm gonna get waterlogged here. Thanks. And the hose on the shepherd's crook, huh? Okay. Or we could build a Ritchie-Chrétien and test both achromatic surfaces with the tester. The Schmidt cast is today's most popular telescope for a number of reasons. It's easy to make it short and fat like a Texas stubby, so that diminishes vibration and weight. Two of the surfaces are spherical, and the corrector plate is a very, very slow surface. It doesn't magnify very much or diminish very much. The Ritchie-Chrétien system is the one that's most often used on big scopes nowadays, and Ritchie proposed it for Palomar, but he'd had a kind of a falling out with George Ellery Hale, doggone it, and so Palomar was built as a paraboloid with a convex hyperboloid for a secondary, garden variety Cassegrain. Okay, So how do we hit the tolerance? Some of you may be familiar with the work of Riccardo Platzek and Ernesto Gaviola, who proposed something they called the caustic test in 1939. And their statement was that the fundamental law of shop optics is that the surface can be figured as accurately and only as accurately as it can be tested. That is to say, don't count on luck. It ain't going to happen. Measure it. If we want to measure 5.6 nanometers or 220 billionths of an inch accurately, we need a magnification of something like 20,000 times. That gives us a span of about 112 microns, or 0.112 millimeters. And we can do that with a screw micrometer, but it's a big magnification. The book has equations and graphs that show this, but they're a little abstruse and too cumbersome for a PowerPoint presentation, and they were the most boring part of the book that I had to do. Okay, so how do we get the evolute of a curve? Some mathematics is involved. There are two evolutes we've got to measure. We've got a figure on. One is the evolute that we have ground of the curve that we have ground into the glass, and the other one is the evolute that of the curve that we want to be in the glass. And the first one is just a matter of shining a laser at the glass, measuring, keeping an eye on what comes back from the glass, and rocking the laser from side to side until we get a maximum return. Then we'll move the laser a little further along the piece of glass and do the same thing and keep going until we run out of glass. And that's going to give us a set of points, you'll see that in a minute, that essentially describe the evolute. And this is the old equation from 9th grade algebra, which I'm sure most of you have forgotten. Y equals mx plus b. The y is the distance across the glass, and the m is the slope of the laser as we get a full return. Okay, so those lines that we get, the mx plus b lines, are going to be perpendicular to the glass and tangent to the evolute. Okay. Let's see how it's done. We got a sort of a process here. Here's my laser head. We have a laser pointer. You can see just the butt end of it here. A sensor, a beam splitter, which if you can see it, your eyes are better than mine. It's glass, so it's transparent. And a micrometer for tilt and swivel. Mainly because I don't like jockeying things by hand, and it makes life much easier if you've got it. The laser head rides on a slope arm, which we'll see in the next slide. The slope arm is one axis, tells you what the angle is, and the other axis is the intercept axis that rides across the width of the glass. We wiggle the slope arm till the laser comes back full strength, and that's a pretty high quality flash. It's not like trying to look through two holes in a Cooter mask and judge whether the shadows are the same darkness. It's quite a bit easier. Okay, so here's what we do. We've got an ellipse here. How do I know it's an ellipse? Well, I made it. And here we have tangent lines to the surface of the ellipse. Those are pretty easy to find. And any line that's perpendicular to a tangent has to be tangent as well to the Evolute. Okay, so here's a bunch of lines that we get by stepping across the optic. Now, point out here that the laser head can be down here and move that far, or it can be right up here and just move that far. The lines are going to come out the same, pretty much. Maybe you'll have a problem with tolerances and accuracy, but not bad. And here's what we do. And these are, remember that all these are brought into the computer as pairs of numbers, slope and intercept, okay? We have here 3 returns from the mirror. The first one intersects the second one at this point. The second one intersects the third one at this point. And halfway between them, we pick the point, and we call that the Evolute. We call that a point on the Evolute. And at the distances and angles, it's pretty accurate. It's pretty much how the gadget works. Okay, let's take a look at the gadget. Here it is. It's on castered legs, so I can move it. And it's not exactly a lightweight gadget. It weighs a little more than a Foucault tester. And right here is the laser head that I showed you in the previous slide. And this is the slope arm, which rocks back and forth. And underneath the slope arm is a follower that runs on a digital readout scale. So I can measure to the nearest, pretty much the nearest, I think it's 100 microns. Okay, now the intercept axis is a ball screw here. It's a 32-inch Lintec ball screw, which means I can measure an optic up to about probably 58 inches. Here's a better view of it. This stepper motor here is the stepper for the slope axis. The laser head is out here. And here's the ball screw for the intercept axis. That's also driven by a stepper under computer control via an Arduino. Okay, now let's go to the hard part. We want to look at the other Evolute, the one we're trying to grind the mirror to match. Okay, so that means I got to change slides. Here's the equation for it. As you can see, as everybody completely understands here, requires a little bit of calculus, a little bit of mathematics, or maybe a little bit of computer programming, which is my forte. I got my living for 60-odd years as a programmer. Okay, and it allows us to produce, to plot the evolute of G of Y, which is the surface of the mirror. And that surface, of course, we denote in terms of the radius of curvature at the center and what all else? The eccentricity of the curve. Now, having this expression here, we can get the evolute of the curve and compare it to what we've got in the glass, and la-di-da, or something like that. We're in business. Okay, now I want to show you a complicated scientific instrument here. It's a circular cross-section cylinder. Don't mind the coffee stains in the bottom. You can ignore those. And the light comes in from this side, and it reflects off the side of the cup onto the bottom. And we have a double lobe curve here, which is, it's mostly resembles a pair of buttocks. Now, this curve tells us a whole lot about spheres and circles. For one thing, the curve of that's a caustic. Curve of the caustic is what we call an epicycloid, okay? And in fact, the cusp of that curve turns out exactly halfway between the surface of the cup and its center. Anybody remember from what the curvature of the focal surface of a Schmidt is? It's exactly half the radius of the sphere. Now, into this, the caustic has an intimate relationship with the reflected wavefront. Okay, the wavefront coming into this cup is nominally a flat one. Coming out, coming off the surface and down to the bottom, it's anything but flat. But that caustic is, in fact, an evolute of the wavefront. And what we're looking at for a telescope is a wavefront that's circular. Because when it's circular, it focuses down to a point. We'll see a little of that in the next clip here. Now, I got a bit of an animation here. And how do I start this again? Can you push the return key or something? Okay. All right. Take an eye. Now there's two. I guess we're going to have to run this again. There's two parts to this, three parts actually. We have a square down here which covers a small amount of the caustic. It's magnified up here, not a whole lot, but some. And the curve of the reflector here morphs from a circle through an ellipse to a parabola to an hyperbola. And right here you see what you get for an hyperbola. It's not, in fact, a caustic, but more like a raptor's beak. And that's why you hear so much cussing when the ATM's got an hyperboloidal figure on his mirror. Okay, let's see. Can I run this again? Is that?
Try to click back and then click forward.
Okay, let's see. Okay, give me probably just an arrow on there would do it. Okay, all right now. That was a parabola, and you saw that the wavefront came to a point, in other words, a focus, and that's what a parabola does if you're on the axis. Okay, now, down in the corner here is a little legend, and we've got the frame count, the angle at which the incoming light is cast on the reflector, and a whole bunch of other things, which, if you buy the book, I'll give you this. But it takes a little bit of looking. Okay, the coordinates of the small box are given in that legend, and there's a yellow cross that ambles along the x-axis from here to here, and I guess in subsequent, and there's another cross, an orange one here, that essentially denotes the extent of the caustic, if you've got a caustic, which you kind of don't after you pass through the parabola. Now, that reflector there is an f0.5, and down here we see the evolute of the curve, and this oddball curve here has at each point the radius of curvature of this curve. The measure from here to here is the radius of curvature. I put that in just because I wanted to see it. Maybe you don't, maybe you do. But it may be worth looking at. Okay, here's the next one. Another copy of the same animation. And now that you've been told what everything's doing here, maybe it's a little easier. Let's go back and okay. Anybody want to see that again? Or is that enough? Okay. Okay. You had a question?
No, I said we're seeing it again.
Good. Okay. So that's pretty much what we just saw. And yeah, we might have missed a few things, but let's take another look at our configuration, and this time let's vary the angle where the incident rays come in. Okay, so here's the same old again. You've seen that enough times, I think, but go ahead and run it if you can. Okay, it dwells on the circle, and it dwells on the parabola, and when it gets to an hyperbola, forget it. Okay, so we might have missed a few things, but that's not real. It's not real relevant. Look at it again 50 times like I have, and you'll find them. Okay. Now, I'm just going to bop through these here. That's the one we've already seen. Here's the second section where the angle to the x-axis varies. And this is very interesting if you're an ATM. Okay, the white line along the bottom here is the angle of the rays, and it varies from -4 degrees, that's this one, down to +4 degrees, and we'll watch what happens to the caustic. Okay. So for the first few bounces, the caustic doesn't change much. And while it's an ellipse, the caustic also doesn't change much until the eccentricity of the ellipse gets to about 0.88, which it hasn't yet. But the caustic just sort of seems to stay there. There's maybe a little change, but not noticeable. If you were looking through a scope with that, you'd probably see the same thing as if you were looking through a spherical primary scope. Now, as we get closer to the parabola, we can watch the tip of the caustic beak just a little bit while it's still an ellipse. And when it gets to a parabola, ooh, that's bad. Okay? That's what we call coma. And it's a feature, not a bug, in a parabola. And it looks a whole lot like an hyperbola. Okay. There's another thing here that was of interest to me, and I hope maybe of interest to you. We'll go and look at a little box at the origin, and note that this beam of light is, in fact, a perpendicular to the mirror, and we'll see that. We'll see what happens to the evolute and the tangent here up here. It's a pretty quick one, but it's about the same as the other. Okay, you can see the white line up here, and it's moved into an ellipse here. And we have the other cross here. I hope you can see that. You know it's where the caustic starts. And as you can see, this thing, when it's negative, goes onto the upper side of the evolute. And when it's negative, it goes onto the lower side of the evolute. When it's positive, it goes onto the upper side. And I guess you could probably get bored with this pretty quickly, but it's edifying. It's something to think about. Okay, so the parabola also has a beak when it's off axis, and so does the hyperbola. The hyperbola has a beak all the time. What do you call it? Coma. All right, and so if there's any question about any of that, please let me know. Okay, now here's the third section of the animation, And this has a much sparser set of incoming rays. It's the same thing. Go ahead and start it, I think. And I apologize for the fact that it takes as long as the other one, but I guess that's science. Okay. And the main feature of this is you can see what is happening to the extent of the caustic here as the thing moves up and down. But the caustic always points at the origin here. Interesting. Center of the sphere. Okay. And here comes the curve. Here comes the cross. And when it hits the middle there, we've got a parabola, and now it's an hyperbola. So, is everybody happy with conic sections now? Okay. All right. Now, the next thing here, the evolute, the curve that generates the evolute is the involute of the evolute. Sounds like double talk, doesn't it? It does to me anyway. Okay, so now we're going to look at a couple of involutes, and what we're going to do is we're going to wrap a string around the caustic. Let's see. Here it is. We're going to wrap a string around the caustic and unwind it. And believe it or not by the scale on this picture, but that caustic is the evolute of the wavefront, which is depicted here, and of course here. It's hard to tell the difference between a circle and an oddball curve like this just by eyeballing it, but the caustic gives us a good read on that. Now, Huygens noted this fact about 200 years ago in his treatise on optics, that the caustic is the evolute of the wavefront. And until I found it there, I thought I'd discovered it. Ah, well. Okay, let's talk a little about Schmidt-Cassegrains now. Here's a genuine Schmidt-Cass telescope. We've got three surfaces. We've got a primary, a secondary, and a corrector plate. And the corrector pre-aberrates the light coming in so that the primary and secondary, which are presumably spherical, can focus it, can make that wavefront circular. And here's one that I've kind of put together. And this is one for mass production. If anybody wants to make them, give me a holler. I'll give you all the documents on them. This is an aluminum primary. Here we have an aluminum secondary, and the corrector plate, since we can make them pretty generally easily, is a substance that's more or less transparent. The stats on this, the primary is a 16-inch f1.5, and the amplification factor is 20/3, which means the final F ratio is f10, standard for Schmidt-Cass. While it's hard to see, the secondary's position is variable along the axis of the system, and there's machinery in here, it's pretty minuscule. Okay, now let's watch what happens, shall we, when a Schmidt camera morphs to an F10 Schmidt-Cass. Here we go. Go ahead and start it for me. Well, wait just a second. Here we have the caustic from its beginning to its end. And down here, this mirror starts as a flat and gradually morphs to a convex convex mirror of about 13 inches radius, which produces that extension of that amplification of the focal length. And here's a bigger picture, bigger this way on the bottom, same on the top. One of the things you should notice about this is that this curve, the caustic, doesn't change by much. And here's the third section where we have a full size here and not so much magnification along this axis. You can't see the primary, well, you can see the primary right there, but you can't see the secondary. And the caustic pretty much stays the same. And this is something I've kind of gone through. There are graphs in the book of the absolute phase of light coming into a primary, hitting a secondary, and going out, or actually starting at a point and hitting the secondary, going to the primary and out to the front, and what the phase is. And it looks an awful lot like those Schmidt curves in ATM 1, I think it is. Okay. So why should we go to any of this expense to build this complex and computer-controlled tester? What do we get from it? What's the ROI? Well, the fundamental of shop optics is that a surface can be made as accurately as it can be tested. And as I said before, don't count on luck, it ain't gonna happen. We get a fair number of advantages by testing the Evolute. First, we don't have to stare past a razor blade. Second, it's a little easier to detect flashes than it is to tell how dark the shadows are. The test is computer controlled, and since the reflection is electronically measured, we don't have to depend on the eyeball to do this. Okay, how much does this tester cost? I don't know. I spent about $3,000, but I was inventing it. A lot of the stuff I bought for it didn't get used in it. A lot of the things I did, you might not want to do. I used a DroPro's digital readout, 2-axis, for measuring everything, and that was about about $1,500 worth of the $3,000. Again, there were a couple of things I didn't use. If you're an ATM, you're probably cheap like me. Aren't all of us? I don't know. So, maybe you don't want to build this all by yourself. Okay, a group of ATMs could put one together, and it wouldn't cost any particular member a whole lot of money. And I have a patent on the gadget, as our colleague here held up, and it's due for a second payment on the fees middle of next year. But if you want to make it and sell it commercially, give me a call. I got no brief to gouge anybody on it, because I've got an ulterior motive here. I have a book. I have a hard copy of it right here in 8.5 by 14 format, and some more back at the car. And that's the first volume. The second volume comes as part of a PDF that has both volumes. I got some, as I say, paper-bound hard copies, not very many right now. And there's a version that's going to come on PDF. And I think the whole shoot and match, including ancillary material like computer programs and things like that, is going to go for probably $25. But I've spent $35 on these, so if you want one right now, I'll give it to you for that, but don't expect any mercy. It also comes with a jump drive. And, well, here's the next thing. Yeah, but I need one good reason to buy the book. Well, think about this. A little bit of science fiction. Are any others here besides me old enough to remember what happened to the dinosaurs? I guess not. Okay, the Planetary Society is worried a lot about whether another one of those asteroids is coming and is going to smack us and maybe make us go the same way as the dinosaurs. If we build enough telescopes and possibly link them together like SETI did, we might find that early enough in its orbit to deflect it, get rid of it, and kind of, you know, save the planet. Okay, thanks very much for listening. Anybody got any questions? Yeah.
Two questions, I guess.
Sure.
One is, there were some brief glimpses of the hardware.
Yeah.
It's completely unclear what's actually going on. Are you pointing light at its surface and measuring where it returns?
I am pointing light at the surface and doing this. Now this is not coming right back to me, so I move it a little bit till it comes perpendicular. Okay, and it returns a maximum return, and that's what I. Okay, yeah, the slope arm on the tester changes the angle of the laser, like like this. It's going through that beam splitter into the sensor on the side of the laser head. Photodiode with an amplifier in it, yeah, and that's plugged into an A to D converter that goes into the computer, and the computer keeps track of those and maximizes the number.
Analog voltage from position of spot?
It's not really the analog position of the spot, it's maximum return. Take your laser pointer and shine it into a piece of glass and watch what happens when it crosses your eyeball. Don't do it too often, your eyeballs are very valuable. But when the return beam comes past your eye, it flashes, it's bright. So there's a high quality return. Peak, right. So,
is there any connection between this and the Gavial caustic test?
there is, and I will be glad to hold forth on that to a great extent. The appendices to the book contain the Gavial Platsek paper and my redaction of it. I studied it, believe it, for quite a while, and I found 3 errors in the math. None of them life-threatening, but you know, nagging. Their expression of the caustic test, it turns out, was a misnomer. They were looking at something akin to the Evolute, but they were noting when the beams from the two sides of the Cooter mask crossed each other on the axis. They were not in focus there by any means. Okay, you have another question?
Yes, how many test points per given area does your machine take?
A bunch, probably maybe 50 across the diameter of a 5-inch disc, a 6-inch disc. It depends a lot on the laser you're using and how wide the spot is.
Yeah.
So I'm using a $1.10 laser pointer, cheap. Maybe with a Heaney laser or something better, you get better mesh than that. Okay. Anybody else? Give me a holler and I'll talk to you about the Platsek Gaviola paper. Yeah.
How long does it test? How long does it take to test, for example, a 6-inch mirror?
Probably less than 5 minutes, maybe a minute, but it's you move, you wiggle, you move, you wiggle, you move, you wiggle, and it's all under computer control, so it's by stepper motors.
It sounds to me like this is a very complicated device that makes testing our optical surfaces extremely easy.
I hope so.
So the idea would, I think, be maybe the Springfield telescope makers ought to build one of these. Francis, where are you? Maybe we ought to build one of these, and then we can experiment with it. I hope that I know Dick Parker bought a book. I hope some of us buy the book too.
Yeah.
It sounds very interesting, and the math seems vaguely familiar to me. Of course, I wasn't that bad in math, but I wasn't 100% in it either. So anyway, thank you for that presentation. I think it's just about enough to get us intrigued and curious.
Good.
And hopefully there'll be enough curiosity around here to maybe build one of these over the next couple of years. Sounds to me like it might take a year or more to just build the device.
If you want to build one, I'll be more than happy to talk to you and coach you through the entire experience, and maybe you can avoid some of the pitfalls I was involved in. Let's see, and it should be a whole lot cheaper than the one I did, and you could possibly substitute interferometric readouts for the digital readout that I've got on it, get better accuracy. You know, there are improvements to be made, by golly. And
Okay, thank you very much.